Welcome back to the 8th volume of our Igniting Research Passion series, hosted by the IEEE WIE Student Branch Affinity Group of the University of Jaffna. In the modern age, where most information is kept digitally, it's important to keep our data safe, protected, and untampered with, especially from cloud service providers who have the potential to be deceptively malicious. That's why today our honored speaker, Dr. Sushmita, who's the Faculty of Engineering Lead of UNSW Institute for Cybersecurity, IFCYBER, and Associate Professor in the School of Computer Science and Engineering at UNSW Sydney, will be guiding us through the topic, Proofs of Storage for Cloud and Blockchains. Dr. Sushmita is a senior member of both ACM and IEEE. Her research interests are in applied cryptography, post-quantum cryptography, blockchains, and privacy-enhancing technologies. She designs practical, efficient, and provably secure protocols that can be deployed in real-world applications. So, without a doubt, she is one of the best speakers to discuss the intriguing and important topic today. So without further delay, we hand over the session to you, madam.
Thank you very much, Cynthia. And thanks all the organizers, Varsha and Nitika, for inviting me to this talk. I will share my screen. Okay, so before I start the talk, I would like to thank the traditional owners and custodians of the land I'm from, and pay my respect to elders past, present, and emerging. So I'll give a little bit context about this work and a bit on how both, proofs of storage have played an important role in both clouds and blockchains. So what I'll do today is give you a brief idea of the importance of these proofs of storage, or giving some way to figure out that the storage is maintained correctly at both cloud and blockchain. So I've been working with cloud and blockchain for a while. And, when I started exploring proofs of storage, it was only in the context of cloud. But later I figured out that these concepts are very nice and important even for the blockchain setting. So that's why I will talk the first part of my talk would be the motivation for proofs of storage for data sharing and how these are used in the cloud setting. And then I will talk about decentralized storage and some applications for that can be used in blockchains. And I will talk a few about some open problems and discuss why this problem is really important as well as interesting. Okay, so we'll start with the concept of data storage. So maybe I'll mention that if you have any questions at any point of time, please interrupt me and ask questions. I am not able to see the chat, but I will request either Varsha or Nitika to let me know if there are any questions so that we can take it as and when we proceed. So storage as a service has been really important in the cloud setting. So what we have is a cloud server, and these could be, Amazon, it could be the iCloud. You typically keep all your some of your documents, photos, and many other files in the storage that's the servers provide, and this has been growing very rapidly. And the storage as a service value continues to increase as we generate more and more data on our end, because we are not able to keep all the information on our local drives. And with this, the importance of secure and reliable storage becomes more and more important. And that is why we want to protect the data integrity when the data is stored in an outsourced server, which we don't have any control over. So when we think of data storage and data sharing, a few questions come to our mind. And we not only want the storage to store our information and use the storage as a service, but we want to ensure that this data is not tampered with. We have seen a number of data breaches. We have seen a number of cases where our data that is being stored on these outsourced servers are being sold to third parties, and we want to protect against all this information, all this fraudulent activities. So the few things that we want to control or want to ensure is that the server is giving us a secure and reliable storage, and the data is either not tampered with malicious intent, or even if there is some failure on the server, this is not affected. We also want data to be accessed only by authorized users, which is a question of access control. And we want to ensure that the data that we are storing on the server is not shared with third parties without our consent. And one of the questions that becomes very important is that is the service provider complying to the regulations that are that they have to comply with. So, for example, there are questions around how the data is stored, used, how it is shared. Do I have the proper authorization? Do I know which geographic location I am sharing my data? And all these questions are actually very important questions, especially when there are important regulations that are the service providers are bound by. So, for example, you would have heard GDPR in the EU, CCPA in the US, Australia. Australia has privacy laws. Several countries have very strong privacy laws as well. So, when we store data, just like auditing documents in any context, say, for example, any organization have to go with numerous audit processes. Similarly, data needs to be audited when it is stored in the outsourced server. And the data auditing is a periodic event to assess the quality and utility of data, to evaluate the security, data integrity, privacy protection, accuracy, and so on. And it has become more and more important, especially when there are so many data breaches. Australia faced a lot of data breaches around, last 2022 and 2023, which has asked for a large number of, regulatory measures to be put in place. So what we need at this point, when we talk about data auditing, is that first and foremost, the data that we have stored on the server is intact. And this is called the proof of data integrity. The data is not tampered with, data is not corrupted. We also need various other proofs, for example, proof of geolocation, which means that the data is stored in the servers within a particular territory. So, for example, GDPR in the EU mandates that the data should be stored in servers which are residing within the European Union. Similarly, there are certain legislation, certain countries which have right to be forgotten. For example, this is prevalent in EU, in India, where they have a right to be forgotten, which means that if data is asked to be removed, it should be there should be a proof of erasure. And we also need protection against data breach. So in this particular talk, I will focus on only one thing. I will focus on protecting the data integrity in the server. So a couple of things when we start looking into checking integrity of data, we think of this as just abstract out the problem. This is on my left is a honest data owner, and the server is where the data is stored. The naive way of doing this is that the data owner keeps a hash of the data and submits the data on the server. And when it downloads the data and checks with the hash that is stored on its side. So it will download the data, check if hash of the downloaded data D prime is equal to the hash value that it has with itself. Now, the biggest problem with this approach is that the communication overhead for downloading all the data is a lot. Though this is very simple approach and the client side storage is very low, the communication overhead is too high because you don't really need to download the data in order to prove that the data integrity is protected. We want some simple technique that even without downloading the data, the client or the data owner can prove, can verify that the data is correctly stored on the server. So proofs of storage has been quite an important question. And what it says is that once we submit the data, we need a proof of storage that ensures that the data is stored correctly on the server, it is not tampered with, or the integrity is protected. So on the right, we see that we can think of the data owner as a data server or the cloud as a prover, which proves that the data integrity is protected. And on the client end, we can think of the client as a verifier who wants to verify that this proof of storage is correct, or verify that the data integrity is protected without downloading the data. What we need is a mathematical guarantee to ensure the accountability of the cloud. And these proofs are rather important. And why these are important is that it's not just the proof of storage, but in general, proof of computation, proof of some activity is very important because it tells the client or the data owner that the server is actually behaving honestly, and it is not behaving maliciously. So a data owner can submit a task. Say, for example, it just wants to compute it can be that it has submitted some data and has asked the server to run a machine learning algorithm and return the model. What it does is that not only does it return the result, but the proof of correctness of the computation. A very simple example, think of two numbers that the data owner wants to add, and the server wants to send the result, and the client does not want to calculate the numbers on its end, but must rely on the result that the server is sending. So in this case, the server is a prover, the client is a verifier, and it gives a proof that the task has been conducted properly by the server. Now, one of the questions that we ask when there is an auditing scheme is that the server, the client should be able to verify quickly. The proof should be short so that it ensures low communication cost. Anyone can verify the process, meaning public verifiability, and the third party performing an audit is unaware of the data, so the privacy preserving property. So what we will do, we started with a simple way of storing the hash and matching with the hash. Now we can look into other ways of doing the data auditing. So for example, you could take some random indices and store only a partial information on the client end, and then store the rest of all the data on the server. And here the big file is broken down into chunks, so you can store a subset of the chunks on the client client end and the full file on the server. And then the client queries randomly a few positions, say 1, 4, and 9, and the server returns the blocks M1, M4, and M9 to the client, and the client verifies with whatever information it had stored on its end. So it will compare the blocks M1 with its local storage, M4 and M9 with its local storage, and be assured that, yeah, I mean, my data is safe. Since it's sending random challenges, the cloud, it is assuming that the cloud does not know what challenge, which blocks it is going to send in advance. So it has to store the entire file in order to pass the audit. Now, definitely, if there is a block that has been tampered with, say block number 10 is tampered with, and this is not queried, you would not know that this block has been tampered. So it all depends upon how many blocks I am I'm querying for. That will improve the probability of success in this case. Now the storage cost of the verifier and the communications cost is pretty high because you're still downloading the blocks and verifying with the client storage. Now, there has been a lot of work on this concept, which is called the proof of data possession, which means that the client, the server has to prove that it possesses the data that the client has asked it to. So one of the naive ways of doing this is to send the message and the signature to the server. And it could be, message or a tag. And the tag is an unforgeable authenticator, meaning that no one apart from the client is able to forge sigma I on the message MI. And then it again sends random indices and it returns the message and the sigma pairs for all the random indices, and the client verifies if sigma I is the correct authenticator for the message I. Note two things. In this case, the client does not store any information on its end. So unlike the previous case where it stores the blocks, it is not storing any of the blocks in this case. But at the same time, it is able to verify looking at the message and the tag pair. Also note that if I am not the client, I will not be able to generate a tag. And the client, similarly, the server cannot generate a false tag on the message. So this is what this is not possible in this case because the authenticator is unforgeable. If in the case of a private verification, meaning that the client is verifying, this sigma I is a message authentication code. And this work has been done a long time ago by Athnes and the group, and this was called proof of data possession. There's also another concept of proof of storage called the proofs of retrievability, which means that prove and recover. So what it means is that the server not only proves that it has stored data correctly, but even if there are some blocks that has been tampered with, the client can retrieve or a client can get back the file that it had asked for. And in this case, the main idea is to have add redundancy to the file by having some erasure codes so that with these redundant information, it is possible to reconstruct the file correctly, even if some of the blocks have been tampered, erased, or modified. Okay. And in this case, again, the rest of the audit performs as before. It's you return the message and sigma pair and verify. Now, in both the cases, the proof size is proportional to the query size, meaning that if I send more indices to check, I will get the proof size to be large enough. The proof size will increase, but at the same time, so this is an extra overhead that is incurred. And this concept was again proposed the same year as the previous one in the same conference. And this is by Jules and Kaliskis. Now, what what has been done since then is that you want to have a way to ensure that the proof is compressed. I mean, the proof size is small, irrespective of the query size. And in order to do this, the main idea was to take all these messages and club together in a way that we are able to generate a sigma, which is also the combined tag for all these messages. So mu is the combined messages and sigma is the combined tag. So why this is useful is that if you send mu and sigma, so the client verifies only once instead of the client verifies only mu and sigma, and instead of sending M1 sigma 1, M4 sigma 4, and M9 sigma 9, now it has only one message block, which is mu, and one tag, which is sigma, and it should verify correctly. The only catch of this case is that how do I construct these unforgeable tags so that the message and the tag pair, they match with one another. And this is also called a linear homomorphic authenticator. So what I will do now is talk a little bit about some of the research that we have done in this space. And one of the questions that we were asking is that, this is all good as long as your file is what's one file. However, we typically do all sorts of operations on the file. We read, not only just reading, we typically modify files, we erase content from the file, we add content to the file. So all this means that the file is dynamic in nature, and the storage proof should also be dynamic. So we did quite a bit of work in this space, which we termed as the dynamic auditing schemes. And I will show you a very simple example why the naive static scheme cannot be extended to the dynamic auditing scheme. And the way we want to do it is that, say, for example, the file block M4 is modified, and say M4 and sigma 4 are the corresponding pairs in this case. So what we want to do is to we upload the M4 and sigma 4 also to the server, because we have altered a block. However, suppose we again do a proof of storage by querying 1, 4, and 9. The server might not change the block. It can still keep the old stale message block and the tag, and it can still pass the audit because the M4 and sigma 4 are the correct message and tag pairs, and so these would verify correctly. So the owner is able to verify. Even if the server does not update files, it passes the audit. So that's the problem with naively using the static scheme to the dynamic ones. And we did a lot of work in this space, and some of the work was supported by NetApp, where we did a lot of experiments on the servers. So one of the things that one of the key points to take back here is that not when we make an update, we need to send a proof of update, meaning that the server should tell the client that, yes, this update has been made successfully. And the next question is that what does this update proof look like? What does this update proof look like? And how can I guarantee that there is data freshness? Meaning that whenever I'm changing my content of the file, this is also taken into consideration by the server and it updates the file accordingly. that was one of the challenges, that we have to protect against data freshness. But we also observed that the authenticators that were used in the storage, in the static storage, are very much linked with the index of the block. So, for example, all the constructions that were used in the static case had inbuilt this I, which is the identifier of the block within the file. And this made it very hard if, for example, I was inserting a new block in the file. So, for example, if I were to insert a new block M4, then all the subsequent indices had to be changed. And what it meant was that all the tags have to be generated fresh. So this was a big challenge for the dynamic proofs of storage. So we realized that there are two issues that we have to incorporate. First of all, that the data freshness had to be guaranteed, and then we needed some schemes which where the index is not bound with the authenticator. So that if there is insertion, we don't need to update all the authenticators that are available later from the I. If we are updating the ith index, if we are inserting at the ith position, then we don't have to change all the authenticators for I+1 at the block to the nth block. And what we did was the first problem where we wanted to have the data freshness, we used a dynamic data structure called a skip list. And I will, I will not talk about the skip list, but I'll just say why this was important is that skip lists are probabilistic data structures. And the good thing about these is that if we insert a block, then you can insert it anywhere in the block. What you have to do is that you have to modify the paths from the root to the leaf where it is being inserted, and then you can keep this, broadcast this leaf to the data owner. So this was a very nice skip list, which was inspired by this work on dynamic provable data possession. However, we had to modify it slightly to incorporate to make it more optimized. Okay, and having these two things, what we did was that we could store the file. We could make we could insert content. We could modify content, and every time we needed a proof of freshness that. To ensure that the server was updating correctly, and then we could do audits as previously. So, I mean, you don't have to look into all these, all this flow, but this is what it says. And when we compared it with the existing work, there was quite an improvement in the computation for the verifier, and also the security was in the standard model, unlike the ones mostly which were on the random oracle model. And when we compared our scheme with the best known static scheme, we had very good we saw a good performance. But this was, the dynamic scheme and all these, and the static scheme. The static scheme is really old. The dynamic schemes were done, in 2020s and so on. So the question is that it's 2024. Are these still relevant? And how can these be used not only in the cloud storage setting, but in the blockchain setting? And having, worked in the space, I thought that maybe, I can look into how these proofs of storage could also be used in the blockchain setting. And This is very important because continuous availability of data is highly desirable. We have a lot of decentralized storage nowadays, which rely on these proofs of storage, because we have to ensure that all the data that is stored in decentralized storage is also they are not tampered with. And then there are some correlations with blockchain scalability solutions that are available nowadays. So I'll talk about two things here. I'll talk about some of the applications of proofs of storage to the blockchains. But I'll take a pause here and ask if there are any questions.
There's nothing in the chat, ma'am,
Okay.
yet.
Yeah. Then we can continue. Okay. So first thing that I will do is talk about, what are these decentralized storage, and give a quick idea of what is what is meant by blockchain. Why do we need to scale blockchain? But before that, let me tell you what a blockchain is. So a blockchain is a distributed, verifiable, immutable ledger, which means that it is a ledger, and it has details of transactions that are performed in the system. It is immutable, meaning that once these transactions are recorded, these cannot be changed. That means it is immutable. Verifiable, meaning that this can be verified, the transactions can be verified. And distributed, meaning that the ledger is not kept in one central space, but it is stored in the network, and the same copy will be stored in multiple nodes in the network to have redundancy. Now, I talked about the accountability problem, and let us revisit the accountability with the blockchain. So if you think previously, what we had mentioned, that the data owner was honest and the client was dishonest. That was the assumption that we had made. But it could be that the data owner is also dishonest, and it can try to frame the server, saying that, okay, no, this did not store the correct data, and either the data owner or the server could be dishonest. So whenever there are two dishonest parties and they are doing a trade, it is not possible unless to have a fair trade unless and until there is a smart contract. Unless and until there is a trusted third party. And in this case, the blockchain can behave as a trusted third party. In a normal case, what would happen is that if you have a person as a client and a server, say Amazon, then if there are any discrepancy between the client and the Amazon, the only thing that we can do is take this issue to the court, and the court gives a final verdict. And here we assume that the court is a trusted arbitrator in these sort of scenarios, which are in the real that we see every day. And so essentially, we have the court, which is actually the trusted third party. What we are trying to do is mimic the trusted third party using a blockchain. And why is this such an interesting thing is that now what we have is that we have smart contracts, which are logical, where that execute some logical statements. And the good thing about having smart contracts on blockchain is that these contracts are not run by one or two parties. It is also actually run by the blockchain nodes, meaning that all the transactions that are all the logical steps that are performed are correctly performed, because we are assuming that there is an honest majority in the network. So how do we ensure accountability? Just like before, we submit the data and the task to the server, and we keep an evidence of that. Either we submit the data or the task, and we keep some evidence of the data on the server. And what we next do is that the server returns the result, and it also gives a proof that it has performed the result correctly. And this proof is verified using the smart contract. Now, note one thing. we previously had a proof, but the only thing we are adding over here is that the evidence of the task that the owner is submitting, which means that the smart contract is going to take the evidence of the data or the task, and it is going to match with the proof. And the data owner cannot deny that it did not store the data or it did not submit this particular task. It is actually at the time, it is keeping that evidence on the blockchain, which means that it is keeping all these evidences on the smart contracts for verification data. So one of the work that we did recently and was with accountable storage with blockchain, which means that we have a lot of data that is being stored on the server, and now we want accountable storage. So both the client and the server needs to be accountable for the service. So both the data owner and the auditor both have to be accountable for the for the storage. And in this case, we took the help of the blockchain and ensured that the blockchain acts as a trusted arbitrator and helps into ensure accountable storage with the blockchain. We also had another important property that the blockchain nodes which were performing the audits know nothing about the data that is being the data that it is auditing. So that's an interesting property, and that's why it's a privacy preserving audit. Now, when we talk about audits, we need to ensure authenticity, extractability, fairness, and privacy and fairness. So these were all present in this in the example that I talked about. Next, we talk about decentralized storage. This has become a very important paradigm now, meaning that instead of the server storing the data, we have storage nodes which store the data. And it has been found that using the storage nodes is much cheaper than storing it in servers. And it also improves the latency. So for example, whenever I'm fetching the data, if I'm fetching it from some local nodes, then it is much faster than storing the data, than interacting with the server, where the server might be in a very different, a different country or a different location. So decentralized storage has been has some important benefits as well. So nodes in the network, they receive incentives for storing the data, and they also have to ensure that they have stored the data correctly. And that is why the proof of storage again becomes very important. And some of the decentralized storage, Filecoin, StoreJ, they do have customers where they have to ensure that the data that is stored on the server is not tampered with. Not on the server, but on their storage nodes is not tampered with. And again, this proofs of storage become very relevant because, again, we need succinct proofs and we need quick verification of these proofs. So one of the ways in which we want to do this is using commitment schemes. Let's talk about this in some let's see how this is done using some new structures which are called vector commitments. So before I talk about vector commitments, what is a commitment? A commitment essentially is it gives us a guarantee that the data that we are sending is actually the data that we had initially that we wanted to. So in this case, we have a prover and a verifier. The prover essentially sends a message, which is you can think of it as a box that is locked, and the verifier verifier gets this locked box. At a later stage, when you can open the box and reveal the contents of the box to the verifier. Note that there are two important properties. The commitment or the locked box does not leak any information about the documents that are inside or the message M. And the binding property, so this is the first property, is called the hiding property. The second property is called the binding property, meaning that you cannot produce a commitment such that there are more than one opening. So means that you cannot have you cannot commit to two different messages. So one of the you cannot produce a commitment that have more than one openings. Also, it would mean that you have two different messages that you can possibly get, which is not possible. And that is not what we want in the first place. We want to commit to a message and then ensure that, yeah, this is a message we had started with. We don't want an ambiguity in that. Now, this is about just one message, but there are there are certain nice structures which are also called vector commitments. And in this case, the vector commitments, we have a vector of messages or M1 to MN, and we commit for all this vector, we have just one single commitment, which is succinct or short. It does not depend upon the length of the vector. And ideally, and what we want to do is to open it at one or more positions. So we give a proof that would open at say maybe the position ith position. And why these are important is that it could actually have, it has a lot of applications, but one of the applications is to is for decentralized storage. And let us take an example how this is applied to a decentralized storage. Is that if you have a big file and you have like chunks of the file in different storage nodes, and what you do is that you store parts of the file in different locations, and then what you would like to ensure that you have one commitment for the entire file, but you are being able to say you have a subset of the file in server 1, second subset of the file in server 2, subset of the file in server 3, and so on. And what you want to do is to ensure that you have a proof that will say that, okay, fine, I have these data in the server 1. And what we want in this case is that we want that, say, for example, if you have M1 and M2, which are stored in the server 1, we can say, like, I'll give a proof that M1, I can open the position, open it at position 1 and 2 to prove that the message has been correctly stored in the server. So what we want is that we need subvector commitments. So meaning that we have a vector, we have a commitment for the vector, but we also have commitments for the subvectors in this case. So it's really nice to see these properties, because nice to see what properties a vector commitment should have in this decentralized storage setting. And some of the work that has been done, that is being done now in the research community, is how to design better vector commitments for different applications, including decentralized storage. So one of the crucial questions is that, can I make this dynamic, and can I add new data, delete data, and so on? And that is still a very open question, because there are no efficient techniques that can do this, can deal with dynamic decentralized storage in the same way as we have seen for the dynamic proofs of storage. Append is easy, but insertion is not easy, and this is one of the questions that that is still open. So I will talk, very quickly, I will talk about other uses of proofs of storage. And one of the use cases is in the decentralized data marketplaces, where we have different buyers so we have the data being stored in different nodes and in a decentralized way. And you have to ensure that the storage servers are essentially are storing the data correctly at their end. And this is very important when we have a data marketplace where we have a lot of data that the buyers and sellers can trade. And this data is not just stored at one place, it is stored in a decentralized way, maintained by different nodes. The second question is that of fair content distribution. And in this case, for example, what we want is that we have a buyer and the seller, and they have some data that they want to, sell. So in this case, if you have a facilitator or just one entity who is storing the data, you have to ensure that the data is stored correctly on that facilitator. The last thing that I want to talk about is that of scaling. And there is this scaling trilemma, which says that scalability, security, and decentralization is hard to achieve altogether. And there has been a lot of work that is being done in this space, better design consensus. One of the ways to scale blockchains is to design better consensus algorithms. But and this has a limitations, meaning that there would be hard forks. So the other school of thought is to have layer 2 solutions, where you have we have a off-chain layer, and the transactions that are done in the off-chain layer are bundled together, and the summary is written on-chain. And there has been a lot of work recently on this layer 2 the blockchains. There are concepts like payment channels, state channels, and also rollups. One of the key considerations when it comes to layer 2 solutions is that what do I do with this data? Because there's a lot of data that is being generated by the blockchain, in the blockchain because there are so many transactions that are taking place. So where do I store the data? And depending upon where the data is stored, it could be on-chain or off-chain. Typically, on-chain storage means that the blockchain is storing a lot of data, which makes it whenever you are writing on the blockchain and it is syncing across the network, it is making it more and more cumbersome. And also, all the nodes have to store a large volume of data. So there are off-chain storage that are also available. And there are different kinds of proofs that are really important, meaning that all the transactions have been done correctly using that needs to be verified. And there are different types of proofs, fraud proofs and validity proofs. I'm not going into the details of each of these that help to ensure that the transactions are correctly taking place. So this is how a rollup looks like, and you have all these transactions. There is a rollup operator, which essentially sequences the transactions and then generates proofs. This would be one or more entities who might be doing that, and then it generates the compressed data and the proof to the server, which then validates the proof on chain. Now, one of the questions that are really important at this point is to ask is that how do I store the data? And can I have an off-chain storage or a data availability layer that can store data correctly? Now, most important, again, is going back to the proof of storage, is that there is a need for the data availability solutions. And there is a need for data availability solutions, and proofs of storage become central piece in these cases as well. to wind up, there are a lot of problems that are present now, and one of the questions that we keep asking is that is these constructions quantum safe? Most of the constructions that I showed rely on assumptions which are number theoretic assumptions which are not quantum safe, and that's why there's a whole lot of open questions even in proofs of storage, is that can I make these quantum safe? The second question is that in the Web3 application, like gaming and various other applications, we have a massive amount of data storage. So how can we make storage efficient data structure, designs data structures which can take care of these massive amount of storage? Then there are questions around data availability problems in blockchains. And the other question is, how do we maintain data in the blockchain that can, data structures for storing the blockchain states. And the proofs of storage become really important here because we need to ensure that whatever data is being stored in whichever place, either it is in another layer, data availability layer, or in archival nodes, or somewhere else, it's important that we have the proofs that the data is intact. There's lots of open questions that we still have, and I will be happy to discuss with anyone who might be interested. Drop me an email, and we can see how to tackle some of these questions together. So with that, I will stop. Just a note that I'm looking for PhD students. So if you are interested to work in applied cryptography or blockchain or post-quantum cryptography, please write to me, and we can chat and figure out how to proceed. And please feel free to drop me a mail if you have any questions or any questions regarding the talk, and definitely please ask me now if you have any questions.
I'll hand over the session to our secretary, madam, and she'll
sure.
Madam, there are some questions that were raised during the registration. So one of them is that if the concept is decentralized storage systems and there are funds needed to implement proof of storage mechanisms, how can the concept of decentralization still be maintained without small organizations not being included and with bigger organizations controlling most of the systems, therefore centralizing it?
Yeah, that's a very good question. So, the main idea of these decentralized storage is that moving away from the big corporations who are having decentralized servers to having more autonomy, and it's really, I mean, if there is a small organization, and you want to develop a proof of decentralized storage, it's not very easy, and you will be competing with the big players, and that is why it depends, like it's going to take time to move into that sort of decentralized storage systems, but it has been found that decentralized storage systems, they are they have more at this point, they are not very cost effective because there are very few people who are using these decentralized storage. But once it becomes more, many more people join these decentralized storage systems, they would definitely be much cheaper. And from the latency point of view, again, as I mentioned, that these could be much more faster than the traditional the servers. The other thing is that at the moment, what happens is that there's all the big corporations, they have their own massive data data servers. So It's hard to beat at this point of time, but again, small steps. And we have seen like these Storage, Filecoin. These are actually some of the players in the market, and they are gradually picking up. So it's a matter of, I think, time. Does that answer the question?
We hope so, madam. Thank you. And one more other question, that is, what are the most significant open problems in proofs of storage research that need immediate attention?
Yeah. So I think the biggest problem is that most of the proof of storage that I talked about, these are all quantum, these are vulnerable to quantum attacks. And recently, with NIST having very strong guidelines about the post-quantum cryptography migration, it has become very important that we think about post-quantum proofs of storage. And I believe that, from my side, I would say that the post-quantum proofs of storage is still a very large open problem, and there needs to be lots to be done in that space. So that's one thing from designing proofs of storage. But I also feel that the proofs of storage are very closely linked with many of the storage solutions that we see in the decentralized world, as well as in the blockchain setting, as I mentioned. So there are a lot of open questions to see how these proofs of storage could be useful for storing a blockchain transaction data, and how to ensure that these data is not tampered with, or any of these is changed. Because if you store everything on the blockchain, it becomes very heavy. So you are introducing another layer of storage, and then you have to ensure that this another second layer of storage that you are asking for is correctly storing all that information. So there's lots to be done in that space to make them more, to see what are the challenges, and also make them more efficient.
Thank you very much, madam. And I think hopefully there are no more other questions. Good evening, and on behalf of the IEEE Women in Engineering Student Branch Affinity Group of the University of Jaffna, I would like to express our heartfelt gratitude to our esteemed speaker, Dr. Sushmita, for sharing her insights with us today. Dear Madam, your comprehensive exploration of data integrity, decentralized storage, and blockchain scalability has truly enriched our understanding and inspired new avenues for research and innovation. We deeply appreciate the time, effort, and expertise you generously shared with us today. Madam, please accept this virtual token of appreciation we have prepared as a small gesture of our gratitude. I would also like to extend a warm thank you to all the participants who took the time to join us tonight. As we come to an end of today's session, it's perfectly okay if you are unable to switch on the cameras, but we request everyone to join us for a group photo. It would be wonderful to capture this moment together. Thank you once again, and have a wonderful evening.
We'll wait for like 1 or 2 minutes for everyone to turn on their cameras.
Sure. I think it's very close to the end of the year, so also it's quite late in the evening.
All right, madam. Thanks a lot.
Thank you very much for the invitation, and thanks for being there. Okay.
Thanks.
Take care.
Yeah.
Bye-bye.
Bye-bye.
Thank you, ma'am.
Thank you.